last time we introduced the concept of stress and strain and true and engineering graphs. And we were saying that the true graph will have more physical representation because it takes into consideration the actual reduction in area during the tensile test. And we said that each region is characterized by its own equations. So first, we divided the graph into three parts. First, we have the elastic region. In the elastic region, we have a linear variation of the stress with strain. So this is driven by the following relation. And graphically, we can determine the value of the modulus of elasticity. We can determine the yield stress, which will be the transition between elastic and plastic regions. In addition, after we find this point, sometimes it will be clear on the figure how to find it. Other times, if it's not obvious where the yield stress is, we can use the offset method as we mentioned. So we just take a value of epsilon equal to 2%. We draw then the parallel line to a line of slope equal to the slope of the elastic region. And we determine then the point of intersection between this line and the curve, and it will give us the yield point. Now, after the yield point, we start with the plastic region. The plastic region is mainly divided into two parts, before and after necking. Before necking, when we investigated the pattern of the profile, we have seen that a good fitting technique will be to use the function sigma equal to k epsilon n. And we can verify this by just plugging the graph on a logarithmic scale. Because if we start from this relation, sigma equal to k times epsilon n, and we apply ln or log for both sides, then we can get that log of sigma is equal to log of k plus log epsilon to the power n. And you know that log epsilon to the power n can be written as n log epsilon. So we obtain then, on a logarithmic scale, we obtain a linear graph. And from this linear graph, we can determine the values of k and n. Okay, now we will do the interpretation of this graph and how we can determine from it the value of n and k. No need to do the logarithmic graph for k and n, because we can also from this graph determine these values. All we have to do is to consider 2 points. So if you take any 2 points of this region, and you can read from the graph, you can read, let's say, the value of epsilon 1. So let's say this is 0.1. And this is 0.2.
بس اونلاين
ليش كل النهار يعني؟
لا بس اول صف برجع ب11 ببلشوا.
Can you please mute your microphones, guys, if you don't have questions? So you have sigma 1 epsilon 1 and 4.2 you have epsilon 2 sigma 2. So now you have just two unknowns, k and n. So you can write in a system sigma 1 equals to k epsilon 1 to the power n, and sigma 2 equals k epsilon 2 to the power n. You can linearize this system if you want by applying log or ln for both sides to find k and n, or also you can say first this is equation 1, this is equation 2. If I divide 2 by 1, so if I do 2 over 1, I get sigma 2 over sigma 1 equals to k will cancel out, and then you'll get epsilon 2 over epsilon 1 to the power n. This equation will allow you to calculate the value of n. Okay, and then once you find n, you replace into one of these two equations, you get k. Now, in general, we don't do it only for 2 points, because if we take more than 2 points, we can get more accurate values of k and n. In general, let's say we select 3 points, for example, okay? Because you might have some variation between the actual curve and k epsilon n. So to get a good estimation of k and n, it's better to take several points, not just 2. So if you take 3 points, for example, you can find the first value of k and n from 1, 2. Then you repeat the same work between 2 and 3. You get new values of k and n. Of course, they should be close, okay? But in this way, when you take several cases, you can take the average value at the end, which will be closer maybe to the reality. Because if you have, for example, for 1 point, bad measurements, or because you know that sigma epsilon is an experimental curve, and this is prone to experimental errors. So in case one of the points were not very accurate, and or it involves high experimental error, to avoid relying just on 2 points to get k and n, we repeat this work several times, and then we take the average value of k, the average value of n that we obtain. Okay. Any question on this? Now, if we want to use the graph of log presentation, okay, log presentation, we can also, in a simple way, get k and n. So you have here on this scale, you have log of sigma, and on this axis, you have log of epsilon. Okay, so what you can do then, you can say the equation, as we said, is log of sigma equal to log of k plus n times log of epsilon. So first, if I do the analysis of this equation, I can find out that n represents the slope of my graph, because for a straight line, the equation is y equals to ax plus b, and then a represents the slope of variation with respect of y with respect to x. So here n represent in this graph the slope of variation of log epsilon with respect to of log sigma with respect to log epsilon. So all I have to do to get n is to go to my graph. I should have a linear variation. I take any 2 points on this graph, and then I determine delta. This is delta log of sigma, and this is delta log of epsilon, and I do the ratio. So I can get that the slope of n is this, if you want, you measure it with a rule, let's say, this distance over this one, I get the slope. Now for K, to get the value of K, okay, on the graph, we know that if I have epsilon, here it's log. If I have epsilon equal to 1, then log of epsilon will be 0. And then for this value, sigma will be equal to K. This is why we say that in order to determine K, we can just look at if we extrapolate the line. Of course, you might not reach in your graph epsilon equal 1. But you can say, I can do extrapolation of the linear curve. Okay. And for this curve, I determine for epsilon equal 1, what is the intersection with this line? And then for this point, if I do the reading on log sigma scale, I can determine the value of K. So here you can read here log of K, and this will allow you to find the value of K. So this is another way to determine K and N. You can determine K and N graphically using the logarithmic scale directly, or you can take the truth curve, the normal true curve, not on the logarithmic scale, and take several points to determine K and N. Okay. So sometimes in some problems, they tell you use this method or use this one. They tell you use the graphical technique on the logarithmic scale. And other times I can tell you relying on the true graph, find the values of K and N. Now, once I find the values of K and N, I can find the start of necking. Because when I find these values, I can plot what is called the flow curve. Okay, so once I have my equation, sigma equal to K epsilon N, I can represent this equation on the graph. And then I compare this equation with the actual graph. I will see that there is a certain separation point between the two graphs. And this separation point will correspond to the start of necking. So this is how I can use the flow curve to determine the start of necking point. Then I consider that the strain hardening zone will be limited between these 2 points. So here, this is my strain hardening zone. Okay. And for the remaining part, it's the necking part. And as we said, it's not desired to reach the necking part because this will weaken my material. So this is the strain hardening zone. Now we'll see together the different possible behavior of materials and how this will affect the coefficients K and N. So as we said, the true stress will increase continuously in the plastic region until necking. In the engineering stress strain curve, this significance was lost because the stress was only based on the original area value and not on the reduced area. And this means that the metal is becoming stronger as strain increases. So in the strain hardening part, you consider that your material is gaining, if you want, it's becoming stronger. And sometimes the strategy is used to enhance the mechanical properties of the material, but without reaching, we avoid reaching the necking zone. So this property of the material is called strain hardening. Now,
Sir, I have a question.
Yes.
Why does the material become stronger when strain increase? Because
look, to continue deforming it, you still need to increase the stress. Okay, so we consider then that higher stresses are needed to deform it, so this material is stronger. because it can sustain higher stresses.
Okay, thank you, doctor.
Okay, while when you start the necking zone with lower stress values, you can continue to deform.
Okay, thank you.
Welcome. Now, concerning the coefficients K and N, K is called the strength coefficient, and N is called the strain hardening exponent. Now, we'll start to see the different categories of stress-strain relationships. So we start with perfectly elastic behavior. So the first type of material are materials that cannot undergo plastic deformation. They will only be limited to the elastic region. So if you plot their stress-strain curve, you will just have a straight line, okay? And in this case, we say that this is a brittle material because it only undergo an elastic region, and we have directly rupture before starting the plastic region. So it will not go through a plastic region. So in this case, this material will only be characterized by its modulus of elasticity. And you can get the modulus of elasticity by calculating the slope of this curve. And in this case, fractures rather than yielding to plastic flow will occur. So at this point, you have the fracture or rupture. And this is characterizing brittle materials as ceramics and many cast irons and thermosetting polymers. Okay. Now, as we said also before, this is not widely used in manufacturing processes because in manufacturing in general, we need to deform, we need to go to plastic region. Let me check your charts if you have any question. George, log or lin both work. You can work with logarithmic scale, you can work with lin scale. Okay, you know that at the end, all rules are common. You have a lot of rules common between log and lin. So both will apply. Okay, you can draw on lin scale or on log scale, same method. Now, the second type of material is called the perfectly plastic. And we'll see together that this behavior is particularly observed at high temperatures. We said before that the temperature will widely affect the behavior of the material, and we'll see this through the comparison of the behavior of a same material for different temperatures. So sometimes when you draw the sigma epsilon profile, you'll observe this. You will have a certain elastic region at the beginning, followed by a plastic region, but in the plastic region, you don't need to increase the stress to produce deformation. So once you reach the yield point, it will deform in a very simple way, okay, without increasing stress. So in this case, this is a particular case called perfectly plastic, because I can cause increase in deformation while maintaining a constant value of the stress. So in this case, we say that in the elastic region, the stiffness is defined by the modulus of elasticity. And once the yield point is reached, then the material will deform plastically at the same stress level. So if you maintain the yield stress level, you will have deformation. You don't need to increase the stress level. This particular case is characterized by a zero strain hardening coefficient and a strength coefficient K equal to the yield strength. Why? Because we said that the strain hardening zone is characterized by K epsilon to the power n. And as you can see here in the plastic region, the value of sigma is constant, equal to the yield stress. So this is equal to the yield stress. And then if I do the analysis here for any value of epsilon, I have that K epsilon n is equal to the yield. So this will lead to n equals 0 and K equal to yield. Okay, so this is a very particular case, and we'll see that metals will behave in this way when heated to sufficiently high temperature. We will define in a while what is recrystallization temperature. So if you heat a metal above its recrystallization temperature, it will tend to behave as a perfectly plastic material. While if you deform it at normal temperatures, at ambient temperatures, it will behave as we have seen before. You have an elastic and a strain hardening zone, and then a necking point. So this is the second mode of behavior. Who can tell me, is this graph, we plot this graph on a normal scale or on log-log scale? How we can know that this is log-log scale or normal scale? What should we look at? Okay, why Mahdi it's the normal scale? Can you justify your answer, Mahdi? Or George? You need to justify your answer. Why it's log-log or normal? In the log-log scale, how you expect to have the variation of sigma versus stress? Okay, look, Mahdi, it's true that the axes are called sigma and epsilon, but in reality, they put for you sigma, but when they present, it's because for the logarithmic scale, you have already on the paper of logarithmic scale, it's designed in a way that the value presented represent log of the value, not itself. Sometimes they put just sigma, but they plot it on logarithmic scale. So when you read a value here, let's say when they put, for example, a 1, if you measure this corresponds to log 1. When you put, let's say, K, and you measure this, you get log K. So to know if it's normal or log-log scale, you should look at the pattern of variation in the plastic region. In the plastic region, if you are representing the true curve on a normal scale, you will not have a straight line. You will have what we call the strain hardening zone, which will be characterized by a curve. And this curve is, you can find its expression by K epsilon to the power n, which is not linear. Since here you have a linear graph, this means that this was represented on logarithmic scale. Okay. So here, this is log-log, log of sigma versus log of epsilon. And you can see that in this case, you have in the elastic region a linear variation, because of course, if the variation is linear in a normal scale, it will also be linear in a log scale. Okay, while if it's following K epsilon to the power n, then it will be linear but with different coefficients. So here in this zone, what is the equation in elastic zone? Sigma equal modulus of elasticity times epsilon. Okay, let us see what will be the behavior in log-log scale. So if you do log sigma, it will be equal to log E times epsilon. So it's log E plus log epsilon. Okay, so still in the elastic region, if you present it in logarithmic scale, it will also give you a linear variation. And what will be the slope of this linear variation? in the logarithmic scale? What is the slope of this line? Yes, exactly, it's 1. Okay, it's 1. So here in a logarithmic scale, you have the slope is 1. Okay. And if you want to find what is the modulus of elasticity, okay, to find the value of the modulus of elasticity from the logarithmic scale, you say that this will correspond to a value of epsilon equal to 1. So you can just extrapolate if you want your graph. So let's say 1 is here, epsilon 1 is here. Okay. And you can do this. This is the line of epsilon equal 1. I extrapolate this graph. Here maybe it will not intersect here. خليني أقربها شوي. Let's say epsilon equal 1 is here, for example. Okay. Then when you extrapolate your curve, you can find the intersection point and you can read the value of E. Okay. So this will allow you to read E on this scale. So for the elastic region, yeah.
Can you repeat this point because I didn't quite understand it?
Okay, I will. Look, let me go back to the previous figure because you have it. Okay. Okay, look. Here, you know that what is log of 1? What is the value of log 1?
Zero, doctor.
Okay, log 1 is 0. Okay. If you are working in the strain hardening zone, we have that log of sigma is equal to log of k plus n times log of epsilon. Okay. And if you work in the elastic region, you have that log of sigma is equal to log of E, okay, plus log of epsilon. So if you want to find E in the elastic region, or you want to find K coefficient for the strain hardening zone, this corresponds to log epsilon equal to what for both cases?
0.
Okay. And log epsilon equals 0 correspond to what value of epsilon?
1.
1. So you say that if I want to graphically determine K or E, okay, I should set epsilon equal to 1 and find the corresponding intersection with my line. So here in this graph, you are representing just the plastic region. Okay, let us represent, if you want, on the same graph also the elastic region. It should be like this, let's say. In general, the slope, always the slope in the elastic region is larger because it's it's easier to deform in the plastic regions than the elastic region. So let's say this will be your graph. Okay, you have an elastic region and a plastic region, and you want from this graph to determine coefficients K and E. Okay, to determine K, you look at the plastic region lines. This is a plastic region line. You expand it and you say, I want to determine the intersection between corresponding to epsilon equal 1, because for epsilon equal 1, if I replace in my equation, this will correspond to log epsilon 0. And then I can read on the logarithmic axis of sigma, I can read what? I can read log of K. Okay, so when you do this here, when you do this line, you expect to read the value of k here, because on the logarithmic scale, when you put k here on the scale, this means this will correspond to a measurement here equal to what? Equal to log of k. Okay. So if you from school you have worked, I think, with logarithmic scales. If you look at any logarithmic scales, it will be divided in a way such that when they put for you 10, if you measure this, it's log of 10. Okay. And if you read k on the scale, this means that this distance is log of k. So this will allow you to directly determine the value of k corresponding to epsilon equal 1. Is it clear now?
Yes, doctor, thank you.
Okay, and you can do the same for the elastic region, because if you have, let's say, in the plastic region, also you have a linear profile with a higher value of E. Okay, so you can read this value of E by just extrapolating. I will reduce it a little تشوفوا الانترسكشن. So I want to choose a line having an intersection on the graph. So let's say this is the line. Okay, you take E for epsilon equal 1, log epsilon is 0, and you get the intersection point. Then you can read the value of E. So you take a line like this, and you say that now if I find the intersection, it will give me the reading of E. So this is log of E. Okay, on the logarithmic scale, the value you read correspond to E, and this distance is log of E. Okay. Any other question on this before we proceed? Okay. Now, so this graph here will represent the behavior in logarithmic scale of a material undergoing elastic and strain hardening zone. Okay, so it's not perfectly plastic, because in the perfectly plastic behavior, whenever I reach the yield stress, I don't need to increase the stress anymore to continue the formation, while for this material, I need to increase the stress to continue the formation. This is why we call it strain hardening. And for the strain hardening curve, I need to define two coefficients, K and N. In this case, K value will be larger than the yield stress, and the value of N will be larger than 0. Okay, while for the perfectly plastic graph, K should be equal to Y, to the value of the yield stress, and N should be equal to 0. Okay, now most ductile metals will behave this way when cold worked. So when I deform them at temperatures below their recrystallization temperature. Now, the other type of tests we conduct is the compression test. In this test, we just apply a load that will squeeze the ends of a cylindrical specimen between two plates, and then compression forces will be applied to test piece and resulting change in height and diameter. So this is similar to the concept of tensile test, but now we do compression instead of tension, and we'll see what are the common features between the two tests and what are the differences. So to start with, the setup is very similar, but what is different now is the way of moving the plate. So if you remember before, this was fixed and we were moving this down. Okay, now we fix this part and we move the upper part down. This will cause compression of the specimen. Now, if also in compression, we can define engineering stress curve, stress strain curve, and true stress strain curve. Now, when we talk about compression, we have two ways to represent it. Or we just put sigma and we add the negative sign to say that it's compression. Or also we can do this. We can put sigma compression. So when we put the symbol C, then we remove the negative sign. So, or we say sigma C equal F over A0, or we say just sigma equal minus F over A0. And F is the load applied and A0 is the original area of the specimen. Now in compression, what will take place is the opposite of tensile test. The area will be increased as you compress your specimen, okay? And we'll see how will this affect the graphs. Now concerning the engineering strain, for the engineering strain, the definition is similar to the engineering strain in tensile test. It's the height at instantaneous height minus initial height over H0. Now, since it's a compression test, you have reduction in height. So H will be smaller than H0. And then when you measure engineering strain, you will get a negative value. Here also, another way to represent is to say that epsilon compression is equal to H0. So when you put the symbol C, you remove the negative sign. So you define it then as H0 minus H over H0. Now, in case on the same graph, you want to represent tension and compression tests, you should keep the negative sign for sigma compression, for sigma in the compression zone and epsilon in the compression zone. While if you are just representing the graph of compression alone, no need to put negative values. You just use sigma C and epsilon C. For example, here, this is a graph representing the stress, the compression stress function of the strain in compression. So since I just put the notation C, I will use positive values. Do you think that this graph is engineering stress curve or the true stress curve? And can you do an interpretation about this behavior? Why it's like this? So let us think about it together. Here you have two zones. You have, first you can detect the elastic zone. So this is similar to tensile test. In the elastic region, you can define the modulus of elasticity, and also you have a yield point, which will be the transition from elastic to plastic in compression. Now, what will be completely different is the behavior after, and now we'll discuss it. I will open another meeting to continue.